Now let's take these free body diagrams that we already drew and let's talk about the net force. So we have a skydiver and his weight is 637 newtons and he's falling freely from an airplane. This is just like the one we did before, except now I've added in his weight. And that's just his force due to gravity, and it's 637 newtons. Okay, and so the net force acting on this this person or this skydiver is just the gravitational force, because that's the only force in our free body diagram. So it's really the only force that's acting on this this guy. And so his net force is just 637 newtons down. Okay, now let's try another one. Now in this one, we have the skydiver. His weight is the same. It's still 637 newtons. But now he's falling through the air at a constant velocity, which means he's reached his terminal velocity. And so remember, the terminal velocity is when your force due to drag is equal to your gravitational force. Okay, so our net force acting on this guy is going to be our force due to drag minus the force due to gravity. And since these both are the same, the net force acting on this guy is 0 newtons. So he's actually in equilibrium. Okay? Anytime you have the net force is 0, you know your person is in equilibrium, or your thing, whatever it is that you're talking about. This one is a little more complicated. We've got some more forces, but let's see if we can resolve it and see what's going on here. So we have, it's going at a constant speed, which means our friction force is equal to our applied force. And it's not floating, and it's not falling through the ground. So the normal force is equal to the gravitational force. And so our net force on the x-axis, let me draw this T where it looks like a T since we're talking about the x-axis. So our net force on the x-axis is our frictional force minus our applied force. And you could also do applied force minus frictional. In fact, that's actually what I prefer to do, because I like the applied force to be in the positive direction and the friction force in the negative direction. And that's just like a personal preference. You don't have to do it that way. It just ends up making, when it's not like this, it makes the calculations a little easier. So our applied force is equal to our applied force minus our frictional force is our net force. Since these two are equal to each other, this is just 0. So in the x direction, our box or our crate is in equilibrium. Now let's look at the y direction. In the y direction, we have two forces acting on it. And we have the normal force, which I like to have as the positive force, and the gravitational force as the negative force. And again, these two are equal to each other. So the normal force minus the gravitational force is going to be 0 newtons. And so this object is in equilibrium in the x direction and in the y direction. Let's try another one. Okay, now in this one, we have our normal force is equal to our gravitational force, which is usually what's going on unless our object is floating or falling through the ground, air or something like that. And then we have an applied force that is greater than our frictional force. Okay, so let's figure out what's going on. If we want to look at the net force in the x direction, we'll take our applied force minus our frictional force. Now, we don't know that they are the same. Okay, we know that they're not the same, but we don't know exactly what this applied force is. So all we know is that we have some sort of force in the direction of the applied force. So on the x-axis, this object is not in equilibrium, and you can see that because this this arrow is longer. This applied force arrow is longer than the frictional force arrow. Now let's see what's going on in the y direction. So we have our normal force. To get the net force in the y direction, we want to do the normal force minus the gravitational force. Okay. And then because these are equal, your net force in the y direction is 0, which means in the y direction, our object is in equilibrium, which means it's only moving left to right. It's not moving up and down, which is what you would expect on Earth where we have gravity and things like that.